This is 2D kinematics.
To start off, I will describe how the first two equations in 2D kinematics are derived. For the first equation, we have a velocity time graph and the point slope formula. Here, the variables of the point slope formula are replaced with velocity as y, acceleration as the slope, x as time, and initial velocity as the y-intercept. For example, this equation can be used to find the final velocity of a drone with an initial velocity of 12 meters per second and an acceleration of 3 meters per second for 9 seconds. Next, for the second equation, we can solve for the distance traveled of an object by calculating the area under the curve in the velocity time graph. Here we can derive an equation by using area formulas. We can separate the area into a rectangle and a triangle. For the rectangle, initial velocity is the width, while time being the length. And for the triangle, time is the base, and the height being velocity minus initial velocity. We can further simplify this equation by recalling the first equation. We can rearrange it so that velocity minus initial velocity equals acceleration times time. Now, since we know velocity minus initial velocity equals acceleration times time, we can replace velocity minus initial velocity with acceleration times time, and then simplify. We can use this equation to find the displacement of a ball with an initial velocity of 2 meters per second and an acceleration of 4 meters per second for 5 seconds.
This next equation is used to find delta x without acceleration or without the slope of the graph, and it is derived from the most basic equation used for finding delta x, which is what we found out earlier. The way it works is by taking the average of the velocities and then multiplying it by the time, which gives you delta x without needing to know the acceleration. Imagine a Ferrari. It goes from 0 to 60 in 6 seconds. You can use this equation to find the distance it traveled in that time. If you look at the graph from earlier, we used the velocity initial times time of the rectangle under the curve, and then we added it to the area of the triangle under the curve. Now, for this equation, we have to find the area of the rectangle outside of the curve, which is velocity final times time. Then you have to subtract it from the area of the triangle, which should be the same as before, which is velocity final minus velocity initial times time, and then multiply it again by 1/2 since it is a triangle. Now this should give you the same delta x as before. Once you have this equation, which should read velocity final times time minus 1/2 times velocity final minus velocity initial times time, you can replace velocity final minus velocity initial like what we did earlier with a times t, or acceleration times time, and then you can reduce this equation to velocity final times time minus 1/2 times acceleration times time squared. For example, when an airplane is coming in for a landing and you want to know how long it takes for the airplane to stop, you need to know how long it took the airplane to stop and the acceleration in the opposite direction.
Right, so in my kinematic equation, which is final velocity squared equals initial velocity squared plus 2a delta x, is derived from two other kinematic equations as presented before. Now the most important thing about this kinematic equation is the time is unknown, but it can be solved for from the kinematic equation final velocity equals initial velocity plus 8t. So when we solve for t, we can plug in the newly founded equation for t into the other kinematic equation. Now we can cancel out two a's and factor out an a completely. We distribute and FOIL, then after that you notice that there's still 1/2, so we need to get rid of that, so multiply the whole equation by 2. Now combine like terms and cancel certain terms out. Then move the negative term of initial velocity to the other side, and the result is the kinematic equation of final velocity squared equals initial velocity squared plus 2a delta x. Now this equation can be used in real life to find the speed of certain objects, more specifically like a car on the road. After a certain amount of distance and acceleration, you can just plug in everything and find final velocity. So in this demonstration, I'll be showing you how to derive the kinematic equation final velocity squared equals initial velocity squared plus 2a delta x from this little video that I have of a tennis ball rolling off a table. Now what we want to solve for is how fast this ball is going whenever it hits the ground. As you can see from the diagram, it is going in a parabolic motion. Now because of this and how acceleration is constant in the y-axis, we can solve for final velocity using kinematics. First, we're going to list out what we know, and that is height of the table, which is 1 meter, the initial velocity of the ball when it leaves the table, which will be 0 in the y direction. We want to solve for final velocity, and we know the acceleration will be 9.8. Now what we don't know is time, and that is pretty much irrelevant when dealing with this kinematic equation because it doesn't matter. Now that we know everything, we can just plug it all in and solve for final velocity. Now after plugging in all the numbers and solving for final velocity, we know that the speed of the ball when it hits the ground is around 4.247 meters per second.
The shooting of the basketball is an everyday action that displays projectile motion, which falls into the category of our beloved 2D kinematics. Earlier within this video, the kinematic equations were discussed. One such equation can be applied to this situation in order to find the final position of the ball. That equation is final position equals initial position plus initial velocity times change in t plus 1/2 times acceleration times the change in t squared. The first step to solving this equation is listing our knowns and unknowns. Our known values are the initial position, which is 0, the initial velocity, which is also 0, acceleration is just equal to g, which is 9.8 meters per second, and the change in time was found to be 0.95 seconds. From there, you can plug in these values into the equation to get final position equals 0 plus 1/2 times 9.8 times 0.95 squared. From there, the equation can be simplified to be final position equals 1/2 times 9.8 times 0.95 squared. And simply all you have to do after that is multiply it all together in order to find your final position, which is 4.42 meters away from the shooter.
This is 2D kinematics.